All right, everybody, please take your seats. Come on in, everybody. So today it's our very distinct pleasure to have an alumni back. Our speaker is Dr. Celia Dalou. She's currently at the CRPG in Nancy, France. And prior to that, we got to know her as a postdoc here. She was a GL fellow for 2 years. And then from there, she went to the University of Texas at Austin and was not as happy there. So we brought her back, and that was wonderful. So we had some more experiments to do. And then she went up to the University of Minnesota in Twin Cities and worked in the laboratory with Mark Hirschman. They had an interesting group. I looked at old pictures. You looked a lot happier there than Texas. And she currently finds herself, as I said, at CRPG. And with that, I will hand it over to you.
Thank you. Is it?
You like that?
Is it okay?
Yep.
Okay. Good morning, everybody. Thank you for coming, and it's really a great pleasure to be back here and to get this opportunity to present this study. So today I'm going to talk to you about redox effects on nitrogen isotope fractionation during planetary core formation. And using this study, the effect of oxygen fugacity on this type of fractionation, I'm going to show you how it can help us trace the origin of terrestrial nitrogen. So we're interested in nitrogen, obviously, because it's the most abundant element in our atmosphere. It's at the base of life. You can find it in life molecules like nucleic acid. You can find it in a great abundance into superficial environment, in ocean, in soils, but also in products from the mantle. So there's nitrogen inside in deep reservoirs. And also, although Earth is the only planet to carry complex life, nitrogen was also measured in the atmosphere of Venus and Mars, and was also measured in a return sample from the Moon and Mars. However, the origin of nitrogen and the timing of its accretion during the initial ingassing, during planetary formation, or was it added later by meteorite or comets, all those questions remain debated in cosmochemistry. So today I'm going to show you a tool that can help us to answer those questions, and these tools are nitrogen isotopic ratios. And those are very powerful tools. You will see, I'm going to show you that nitrogen isotopic composition are very variable among the solar system, and so they can be used as tracer. Instead of really talking about isotopic ratio, I'm going to talk about the delta 15N notation, which is a deviation between the isotopic ratio of a sample compared to that of a standard. And for nitrogen, the standard is the atmospheric molecular nitrogen. So by definition, the Earth's atmosphere nitrogen composition is at 0 per mil. The mantle isotopic composition has been estimated to be -5 per mil based on fibrous diamonds. And the surface of the Earth, the sediments, the crust, the altered oceanic crust, have a positive delta 15N averaged around 6 per mil. And so far, those ratios, those compositions were used to trace nitrogen within the deep Earth. So for example, here you see that OIBs are more positive, have delta 15N more positive than Middleton-rich basalt. And that was interpreted as the fact that sediments like positive material were recycling into the Earth. So this is the type of variation you get for the Earth. When you look at the solar system, here you have the 0 per mil, the terrestrial value, and here you have the values for the inner solar system bodies. Here you have the meteorites, and here you have the comets. So it's been thought for sometimes that the terrestrial nitrogen could come from comets, but you can really see here that their nitrogen 15 is very positive. It's too enriched in nitrogen 15 compared to terrestrial nitrogen. But when you look at chondrites, although their composition is variable, they're closer to the terrestrial nitrogen value. Now, there is some sort of consensus that the Earth was built from a volatile poor material, Ancetite chondrite type, so material from the inner solar system, and that the volatiles were added later via material that are more volatile rich from, for example, carbonaceous chondrite that are material from the outer solar system. But when you look at the nitrogen isotopic composition of the carbonaceous chondrite, they are way more positive than the bulk silicate Earth. So the carbonaceous chondrite are too nitrogen 15 enriched compared to terrestrial nitrogen. But if you look at ancetite chondrite, their composition, they're the only chondrite that have a negative delta 15 N value between minus 45 per mil to minus 15 per mil. And those values, although they're a bit below the bulk silicate Earth value, they correspond to some measurement done in deep Archean diamonds, where this range of values were measured. So if the ancetite chondrite are the source of terrestrial nitrogen, how do we explain, how do we go from those very negative value to the minus 5 per mil value of the bulk silicate Earth? Associated to this question, there is the question of the missing nitrogen. So you may be familiar with this diagram. Here you have the abundance of different volatile carbon, nitrogen, water, and noble gases of the BSE normalized to chondrite. And what this tells us is that compared to other volatile, like carbon and water, nitrogen is depleted in the bulk silicate Earth. And this depletion has been interpreted to be caused by the fact that nitrogen may be trapped in the Earth core, because nitrogen was always supposed to be siderophile. So one tool that we have to check if we can have nitrogen in the core is mineral physics. In this very recent study, they showed that nitrides are stable at core pressure. So it's possible to have nitride in the core. But although they put 10% of nitrogen in the core and show that that was in agreement with the PREM model. But obviously, you cannot have 10% of nitrogen in the core, even with the carbonaceous chondrite source. But that tells us that, that nitride could exist and that nitrogen could be present in the core. Another tool we have is experimental petrology, is running high pressure, high temperature experiment, and then measure the partitioning of nitrogen. So measuring the concentration of nitrogen in metals and in silicate. So for that type of experiment, we put ourselves in the condition of the core formation. So you have a magma ocean, and in this magma ocean, the metal is going to segregate and sink to form the core. For this type of experiment, you need to be in very reduced condition because the magma ocean was reduced. And so in those reduced conditions, there is not much oxygen available. You are at low oxygen fugacity. So we placed ourselves underneath this buffer called iron wustite, which is an equilibrium between reduced iron and wustite. And so we put ourselves below this equilibrium at a few logs unit to be in reduced condition. And so there is a lot of different models on the evolution of the oxygen fugacity condition of the magma ocean. This one is quite graphic. It's from Ruby et al. 2011. And that shows us that despite the type of model that you choose for accretion, homogeneous accretion or heterogeneous accretion, the magma ocean went from very reduced condition, so 3 to 5 logs unit below the iron wustite buffer, and that the oxygen fugacity increased in the magma ocean. So that's why when we do, and when you look at nitrogen, and when you do experiments with volatiles, since following those type of models, volatile are created pretty late in the history of the magma ocean, the condition to do experiments with volatiles are chosen to be between iron wustite -4 to iron wustite. So that's what is done in most study. We place ourselves in reduced condition between the iron wustite buffer and a few logs units below this buffer. We experimentally tested a lot of different PT condition and various silicate composition for the magma ocean and different metal alloy composition for the core forming alloys. So here are all the studies done on the subject since 2011. And here is the way we represent our data. So the partition coefficient, metal silicate, and here the oxygen fugacity. And this is all the data we had up to 2017. Now, 2 years later, we went from 30 data points to more than 160 data points. There is 2 very active groups working on nitrogen partitioning. It's how people get interested in partitioning in the core those days. So you see there, you have some scatter here caused by different type of PT condition or melt composition. But what all those study tells us is that even you have some scatter, the oxygen fugacity remains the main control on nitrogen partition coefficient and on nitrogen behavior in general. And what that also tells us is that at condition around iron wustite -2, you see that the partition coefficient of nitrogen are inferior than 1, meaning that the nitrogen is lithophile. It means that it's going to stay trapped into the magma ocean during the differentiation. But above iron wustite -2, you see that nitrogen partition coefficient is superior than 1, and so that nitrogen is siderophile, meaning that in the late stage of Earth differentiation, some nitrogen could have been trapped in the core. So now we've looked at partition coefficients, so elemental ratio between the metal and the silicate. Now we're going to talk about nitrogen isotope fractionation, and that is noted like this with the cap delta 15N. And so we're looking at difference of isotopic composition between the metal and the silicate. Here, to analyze this isotopic composition, we used to do it on a normal gas static mass spectrometer, which is a machine that we have available at the CRPG. So basically, to do that, we need to separate the metal from the silicate and extract the nitrogen contained in those 2 phases. For the extraction, we use a CO2 laser, so we're going to melt each phases separately. Then the gas extracted goes through a purification step, so you remove all the methane, all the CO associated in those gases, and measure and send only the nitrogen into the mass spectrometer. So that was what's done for this study. The first results on nitrogen fractionation between metal and silicate that was published in 2016. So those data are from a Biret group that did all the experiments between 1.5 and 7 GPa and 1600 to 1800 degrees C. And then they send the samples to the CRPG to be analyzed. So those are the results they got, expressed as a function of temperature. Here at 0, you have no fractionation. And what you can see here is that there is actually a fractionation averaging around -4 per mil. But this was done with the old mass spec that we had at the CRPG, so there is large error bars. We have a new one now. The size of the error bars are divided by 10. And the problem here is that you see no variation with the temperature, which is a bit curious, right? Because if you look at the theory, isotopic fractionation are inversely proportional to the square of temperature. So on a 200-degree difference in temperature, you see nothing. And the main concern I had with this study is that it was done on a very narrow range of oxygen fugacity, not representative of core formation oxygen fugacity conditions. So our study was to test the effect of oxygen fugacity on the nitrogen isotopic fractionation. And we wanted very large sample, like it was an exploratory study, right? So we wanted large samples. So we did our experiment at 1 GPa and 1400 degrees C on the piston cylinder. Our range of oxygen fugacity was 3 lots unique below the iron Woods type buffer to the iron Woods type buffer. And we used iron-rich basalt as a starting composition that we doped in silicon nitride. So here the silicon nitride was used both to enrich our composition in nitrogen and as a reducer, because it has a very strong reducing power. So we obtained a series of basaltic glasses in chemical and isotopic equilibrium with metal alloys composed of iron, carbon, and nitrogen. Here, the carbon is from the graphite capsule. And among all the series of experiments that we did, only 5 samples were suitable for ion probe analysis. Because I'm going to show you that we developed a method to analyze nitrogen content and nitrogen isotopic composition on an ion probe that is possible only if we dope our starting material with nitrogen 15. So for that, we used like a new method that got published last year, in which nitrogen is measured under the form of NO. And with a resolution of 14,000, we can actually separate the NO peak. Here you have nitrogen 14, here nitrogen 15, from the hydrides. And in the meantime, we also developed a series of standards that we're happy to share with everybody with the various nitrogen content. And the absolute value were measured on the mass spec available at the CRPG. For the metal, so this is a bit simpler because the nitrogen in the metal is measured as CN, which is like a common thing people do on the ion probe to measure nitrogen and nitrogen isotopic composition in diamonds. So that was not too difficult, but the standards are a bit difficult because we analyzed them first on the SIMS and then burned them into the mass spec. And that's how we got the nitrogen content and the nitrogen isotopic composition of the metals. So those are the results for the nitrogen content. And the results of the SIMS analysis. We did up to between 3 and 7 analyses per phase, per sample. And we saw that nitrogen was completely homogeneous, both in the silicate glasses and in the metal blobs, and that the isotopic ratio we measured on the SIMS were also completely homogeneous among phases. And because the samples were spiked in nitrogen 15, we got very low analytical uncertainties. A way to check if our method is reliable was to compare our partition coefficient with the literature data. And here are the blue diamonds, our results compared to the literature. And you can see they fit very well with all the literature data. Those data were determined by electron microprobe. And here are the results for nitrogen isotope fractionation. So what you see here are like oxygen fugacity. Here you have the delta 15 and normalized for all the samples, normalized because I use different amount of nitrogen 15 spiking. And here you have the results for the silicate glass, and here the results for the metals. And here the difference between the two is the nitrogen fractionation. What you see here is that with oxygen fugacity decreasing, you have an increase of the delta 15N of the in the silicate glass, and a decrease of the delta 15N in the metal. And that means that during metal segregation, you enrich the metal phase in nitrogen-14, which is completely in agreement with the theory of equilibrium fractionation. The lightest isotope goes into the most reduced phase. So we checked the effect of nitrogen spiking, right? Here are the different initial nitrogen 15/14 ratio put in the experiments. And you see that there is no relationship between the nitrogen fractionation and the nitrogen spike, the nitrogen 15 spiking. So we have no effect on of the spiking on the nitrogen isotope fractionation between metal and silicate. So in all the experiments working on nitrogen, since nitrogen is very volatile, we have nitrogen loss during the experiment. On all the studies that I've showed you, they were between 60 to 80% of the initial nitrogen loss during the experiment. That is because we use graphite capsule to be under reducing condition. And so we needed to check the effect on of nitrogen loss on nitrogen isotopic fractionation. Here, the blue diamonds are our results measured, is the delta 15N measured in the silicate. And here you have the fraction of nitrogen remaining after the experiment. What we did is that we model a Rayleigh distillation model, so kinetic fractionation by diffusion of if nitrogen was lost as NH3 and here N2. And what you see is that our data in the silicate could be explained by nitrogen loss in the silicate. So here either nitrogen 14 went into the graphite capsule or was partitioned into tiny nanobubbles that we actually didn't see. So there is an effect, there may be an effect on nitrogen loss, on nitrogen isotopic fractionation. There is actually two ways now to explain our data. Here, if the nitrogen loss is the reason of this increase, then the isotopic fractionation is only produced by the effect of metal segregation. And the actual isotopic fractionation here what is noted cap delta star. But maybe this increase here can only be explained by the fact that nitrogen 14 is partitioning into the metal, so the silicate get enriched in nitrogen 15, and that this fractionation here is the real fractionation. And here it's going to be, in the next slide, it's going to be noted in blue and the regular cap delta 15N. So here are the results. You have here the nitrogen fractionation depending on the FO2. Here in blue are the non-corrected results. And here in pink are the corrected results. And here you have the data from Lee. So our data are actually converging at iron-wustite to their data. What does it shows here is that during metal silicate fractionation, the metal is going to pump the nitrogen 14 from the silicate phase, and that this fractionation is correlating with the oxygen fugacity. But the big question is why is it so large? It's huge. It goes to minus 250 per mil. This is extremely huge. When we compare with other tracers of core formation, you see that it's around 1 per mil, or never above 3 per mil. So why is it so large? So to understand it, we have to go back a little bit to the theory. Here's the equation of nitrogen fractionation that I showed you before. But this fractionation can also be explained depending on the coefficient factor, the factor of fractionation. And this factor is the nitrogen isotopic ratio in the metal divided by the nitrogen isotopic ratio of the silicate. When you go back to the theory papers, you can see that you can actually write this factor depending on like many thermodynamic constant, and to simplify it, we put all the constant as a little c here, And here you see that it depends on it's inversely proportional to the temperature. And it depends on that, the force constant in the metal and in the silicate. But this constant is not actually a constant, right? It depends on the bond force, and so on nitrogen speciation. To be a bit clearer, here in the detail, this supposedly force constant depends on two variables. Here, the vibrational frequency, and here the reduced mass. The reduced mass is a simple ratio of atomic masses, and when you look at different speciation of nitrogen, you see that if nitrogen is dissolved as NH, its reduced mass is going to be 1 atomic mass unit, but as N2, it's already 7 atomic mass units. So you already have a factor of 7 depending on nitrogen speciation. And the vibrational frequency, it's something that we can measure using Raman spectroscopy, FTIR spectroscopy. It depends on the bond force. It depends on the bond length, on the charge, on the mass of the isotope involved in a molecule. So it will depend on the speciation of the isotopes. So to illustrate that, I take the example of sulfur. So I'm going to compare two volatile elements that are siderophile. And so here are the data from Jabran Labidi. He did this study when he was a postdoc here at GL. And he did experiments over a large range of PT condition, large range of composition, and in the same range of oxygen fugacity as we did. So we can compare the two studies. And the maximum fractionation he saw was 1.2 per mil. So very different, very smaller than what we actually measured. So obviously there is a mass difference between nitrogen and sulfur, but this mass difference is only 2.5 times. So that cannot explain the large difference that we see between the two studies. But if we look at the vibrational frequency, we can actually learn something. Here are two Raman spectra of sulfur in iron metal, and here in silicate glasses. What you see here is that sulfur, in both cases, both in the silicate and in the metal, will form CAS or MgS or iron S bonds. And they're all vibrating at the same place, both in the silicate and in the metal. So there is only a few centimeter difference between the two phases. But when you look at nitrogen in the metal dissolves as FeN, so quite comparable to the sulfur that vibrates at 330 per centimeters. But the particularity of nitrogen is that in the silicate glasses, it will bond with hydrogen and form NH vibration. And those vibrations are between 3150 and 3350 per centimeter. So here you have a difference of 3,000 per centimeters difference. Sulfur a few per centimeters, for nitrogen 3,000 times more. And when you look at the reduced masses, it's the same thing. You have quite compared those reduced masses for the sulfur molecules, MgS, CAS, and FAS. So you have similar vibrational frequency and similar reduced masses. So the difference between the force constants between the two phases, between the metal and the silicate, is very small. And so you get very small isotopic fractionation. In comparison with nitrogen, here you have a large difference of vibrational frequency, and here you have a factor of 11 difference in atomic mass unit for the reduced phase. So you have large variation of vibrational frequency, large difference of reduced masses between the metal and silicate. So here, the force constant of the metal will be very different from the force constant in the silicate. So this difference here is going to be very large, and so you get very large isotopic fractionation. So this is another example for the skeptics. I'm comparing nitrogen fractionation, but in two different systems. One system is hydrothermalism, and the other is our study of metal segregation. So this recent study studied the effect of hydrothermalism of a metagabro. So basically what's happening when the nitrogen contained in minerals, we lose it to a fluid. Here they determined that the fractionation was around 8 per mil. So again, very different from what we measured. But here, the speciation of nitrogen in minerals is as NH4 plus. And the speciation of nitrogen in the fluids is NH3. So really, the difference in vibrational frequency is only of 150 or 200 per centimeter. So again, 20 times lower than the difference in the metal silicate system. So I hope I convinced you of why we measured very large isotope fractionation for nitrogen. Now, why is it changing with FO2? So for that, we have to look a little bit deeper into the type of nitrogen speciation in silicate glasses. So those are results from a different study where we put more nitrogen into the silicate glass, so our Raman spectra are way better. And that allows us to look at what kind of parameter can control nitrogen speciation in reduced silicate glasses. So here you have the Raman shift, here the intensity. Here you have an air signal to show what would be the signal of atmospheric nitrogen during a Raman analysis if it was contamination. So here you have the N2 peak from the air, and here you have the N2 peak that we measured into a reduced silicate glasses. Here at condition IW, and here IW minus 2. So we can have N2 dissolved into reduced silicate glasses. And this is a different part of the Raman spectra, where you see different kind of molecules. Here you have CH molecules, here you have NH, OH, and H2 vibration. What that tells us is because this signal is so huge and it varies depending on different parameters, it varies among our samples, we can actually fit the area below this Raman spectra and determine why this intensity is changing. So those are the results. So it's Raman now. It's not quantitative. It's only qualitative. But what we see here is that it's the ratio of the area below the NH peak and here below the N2 peak. And what we can see that controls it is first the temperature and the hydrogen fugacity. And here the hydrogen fugacity increases with, of course, hydrogen content and decreases with FO2. So basically what we're seeing here is an increase of the NH over N2 ratio as you go down in oxygen fugacity. So why is it changes the isotopic fractionation? Well, we go back to our vibrational frequency. Here the difference in vibrational frequency when you have nitrogen dissolved as N2 is smaller than when nitrogen is dissolved as NH. Same for the reduced masses. The difference here is way smaller than when nitrogen is dissolved as NH. So with decreasing FO2, you increase the NH over N2 ratio, and that produces large nitrogen fractionation, larger with decreasing FO2. So what are the implications of those results for core formation? Well, we're going to look at the evolution of the delta 15N of the mantle during core formation. So we're increasing the proportion of metal silicate in calibration. Here, this gray bar is the present-day mantle delta 15N value determined from the fibrous diamond. And here, as I said in introduction, carbonaceous chondrite are enriched in nitrogen 15 to be likely the source of the Earth nitrogen. So we're going to work with the enstatite chondrite assumption. Here we took the most extreme values for the measured in enstatite chondrite, minus 45 per mil, and here minus 15 per mil, that we put into a model for core formation. Here you have the isotopic fractionation that we measured in this study. And here you have the total mass of nitrogen in the mantle versus the total mass of nitrogen in the bulk Earth. And this total mass depends on nitrogen concentration in each reservoir. So it depends both on the starting concentration of nitrogen that we can take from a chondrite. Here is the changing mantle over mass of the mantle over the total mass of the Earth. So it's decreasing as the core forms. And here you have the partition coefficient of the nitrogen that we determined. And so here, nitrogen partition coefficient, so the composition, the concentration of nitrogen in the mantle, and the fractionation, the isotopic fractionation, all those vary with the oxygen fugacity. So here are the results. You have the different model depending on the starting composition. So obviously, it's very dependent on the starting composition of the primary material. But here, what you see is different model depending on the FO2. And what you see is that we can model a mantle with a minus 5 per mil value, just starting with an enstatite chondrite source for nitrogen. So obviously, this study was very exploratory. When we started, we didn't know that we were going to have such great fractionation. So we were actually using those samples to develop a method, analytical method. So we need to explore this relationship we found of nitrogen isotopic fractionation with FO2 over a much larger range of PET conditions. And this is now possible thanks to our development on the ion probe. So we can measure both the nitrogen content and the nitrogen isotopic ratio in really small experimental sample, even diamond anvil experimental samples. Although we can actually make some prediction on the results on the effect of PT condition using the theory, we know that nitrogen isotope fractionation will decrease with increasing temperature. And we know that because pressure increases the bond stiffness, and so the vibrational frequency, it will increase the isotopic fractionation. Yet this effect needs to be quantified. Probably the effect of pressure, you can see it when you do experiments over a large range of pressure. So in conclusion, we saw a strong dependence on nitrogen isotopic fractionation with the FO2, and we highlighted the role of nitrogen speciation in the magma ocean on metal silicate nitrogen fractionation. And we determined the fundamental effect of the FO2 on the evolution of the mantle delta 15N value. And so the mantle day, the present day mantle's delta 15N value can be explained by core mantle differentiation if the enstatite chondrite are the source of terrestrial nitrogen. But the thing I wanted to finish with is that since we, even at high temperature, at 1400 degrees C, we measured so large variation, so large fractionation for nitrogen, then nitrogen cannot really be used as a tracer of source rather than a tracer of planetary processes. So this difference that we can have inside, between Earth's reservoir or even between different solar system reservoir, we have to ask ourselves, are they really caused by different source or by different processes or both? Thank you for your attention. Oh, that was quench material. Quenched from the experiment? Yes. It's not in situ measurements. Right. Do you think that that's comparable? It should have an effect because we see it when we do HDAC experiments. We see a shift of the Raman peaks, but not thousands of per centimeter. It's going to be a few, but not much. And my second, you said in one of your slides that the experiment, but then you showed So I tested this effect, but then I did a mass balance, knowing how much, what the initial ratio was, and then what I measured in the metal and then the silicate. And I don't need to have diffusion. It's like the nitrogen loss had no effect, really, because if I don't consider any nitrogen loss, any nitrogen fractionation caused by nitrogen loss, I go back to my initial ratio. Mm. Yeah, I don't know when it happens though. I don't know if it. Yeah, I don't know when it. Yeah, yeah, I don't know. Mm-hmm. Yeah. Yeah, I haven't done it. The Raman data on those spectra are really noisy, and I cannot see nitrogen 3 minus. I don't know if we have some SIN in the experiments. It's hidden below the silicate signal.
I'm just curious,
Yeah.
big cloud of data points with that, all that data.
Yeah.
Stick a slope on there. What does it tell you about this? Second question is related to what it not.
Mm-hmm. Yeah.
Progressively more negative.
Yeah.
So you can't really apply it
Yeah.
without knowing what that.
Yeah, I was curious about that, and I don't know when it happens and what will be the effect. Why then we see such a linear correlation with the FO2 if it's only an effect of the nitrogen loss? Oh, all the experiments were 6 hours, so it's yeah, 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 yeah. We haven't done like a time series study yet.
So the first one,
Mm-hmm. Um, so it's really difficult because either it's from an gas reservoir, so that kept the pristine delta 15N value, but then it's difficult to imagine that then core formation didn't affect this reservoir if it fractionates so much. So it's
they're in mantle lithosphere,
yeah, yeah. Do you have noble gases value on them too? Yeah.
So what's happening?
Or or it's fractionation, like depending on the fugacity of the fluid that makes them. Mm. Okay.
Nitrogen in the fluids.
Okay. I don't know.
Can I comment on that
Yeah.
very quickly? Because based on the partition coefficients, you actually should be something to think about.
Yeah.
The hydrogen fugacity is very
Air. It's just contamination from the air. So I didn't put anything, but among all the samples, we're at 1,000 ppm, and it's very constant. But I did the same type of experiment in Minnesota, so quite a different weather, and I could reach 1% of water, just not adding any water, just from air contamination. So that's quite like it's a parameter that is very difficult to control.
That's 10% in BC.
yeah, in the back.
Yes. So the partition coefficients, they change with FO2, not because of something happening in the metal. When you look at the concentration in the metal, they don't change with the FO2, only with PT conditions. But so it's only controlled with nitrogen solubility in the silicate phase, and that changes, like the speciation of nitrogen changes with the FO2.
I have one question and one comment. And so when you look at your
Yes. So the explanation is that we have actually little micro inclusions of carbon in the metal, and that since we're calculating the nitrogen from the CN, if the carbon signal is really changing over the cycles of the analysis, that's going to create a large uncertainty on the isotopic ratio we're calculating. We're getting from the SIMS.
the silicate part, which is supposed to
Yes, same thing. Yeah. Yeah, the signal is a bit, like for very low FO2, the signal is a bit changing. And also the hardest thing is that at those low FO2, for some reason my metal blobs are smaller. So it was actually quite difficult to measure it using the SIMS. Like you have to have a very small beam size. So we managed to get down to 7 microns in diameter, but that was the minimum. So it's quite challenging still, even if we can do it in situ.
So my comments is really for the pressure effect and
Yeah. Um, I think they were higher solubility than that we have in the silicate. The change in NH over N2 is with the FO2 is identical. It's the same. Um, yeah, yeah. I don't remember. It's I think it's they go to 2 weight percent in the sodium silicate composition. Yeah. We actually have a PhD student working on nitrogen solubility at 1 atmosphere. And he did a large range of NB over T composition for his silicate. And he can actually extrapolate to very mafic composition. And he really see that the nitrogen solubility increase towards those compositions. So that should change. No, in silicate. So then when you have a metal silicate equilibrium, if the partition coefficient is mostly controlled by the nitrogen solubility in the silicate, that should change the partitioning. How that would change the isotopic fractionation, it's still something that we need to check.
Further questions? Thanks, Celia, again. Thank you.